The measurement problem. Traditional quantum mechanics suffers from several issues with measurement. To begin with, it is not clear in traditional quantum mechanics why one can derive a probability distribution from a wave function. Born came up with a simple mathematical process to do so, but there is no theoretical justification for it. It's simply stated as an axiom, an unjustified assertion. The philosophical problem is like this. Consider an experiment in which a particle is prepared to be in a superposition of two states. If quantum mechanics is universally applicable, then we must also consider the measuring apparatus as a quantum mechanical system which interacts with the experimental system. The result of this process, according to traditional quantum mechanics, would be that the superposition expands in a sense. Instead of just the particle being in superposition, the measuring device plus the particle would now be in a superposition. One might imagine that a person observing the measuring apparatus might also become part of the superposition, and so on and so on. Bohmian mechanics easily dispenses with both the issues just mentioned. The key difference is that traditional quantum mechanics insists that the wave function is a complete description of reality. If that's so, we're stuck with those issues. However, Bohmian mechanics suggests that that picture is incomplete. It posits that particles always have definite positions, in addition to a pilot wave that influences them. If particles always have definite positions, then superpositions aren't physical states but mathematical artifacts. Bohmian mechanics includes an equation that describes the movement of the particles alongside the Schrödinger wave equation, which it shares with traditional quantum mechanics. A mathematical analysis of these equations together yields Born's rule. Instead of needing to assert the rule as an axiom, it arises naturally in Bohmian mechanics. It's unfortunate that during the earliest stages of quantum mechanics development, scientists were under the false impression that theories like Bohmian mechanics could not work. For this reason, the theory was ignored for decades. In the 50s, it was shown that Bohmian mechanics does provide a realistic and concrete alternative to traditional quantum mechanics. But despite all the work that has been done on and with the theory since then, many misconceptions and misrepresentations of Bohmian mechanics and its progeny are widespread. I'd like to add a note here about how we judge competing interpretations of quantum mechanics, given that experiment cannot decide the issue for us. As I've tried to describe, Bohmian mechanics, in a sense, replaces a fundamental axiom of traditional quantum mechanics, Born's rule, with the so-called guiding equation. The math of a traditional quantum theory includes, at bare minimum, the Schrödinger equation plus Born's rule, whereas Bohmian mechanics is the Schrödinger equation plus the guiding equation. In traditional quantum mechanics, Born's rule is a necessary addition to the Schrödinger equation to make predictions. But as to why the Schrödinger equation or Born's rule operate the way they do, little to nothing can be said. This fact has been famously reinforced by pithy statements by quantum pioneers, like, "If you are not completely confused by quantum mechanics, you have not understood it," John Wheeler. And, "I think I can safely say that nobody understands quantum mechanics," Richard Feynman. However, Bohmian mechanics does allow for us to at least begin making sense of how the quantum realm behaves. It dispenses with Born's rule as an axiom and instead includes the guiding equation, whose physical interpretation is clear. It describes the trajectories of the particles. Bohmian mechanics likewise clarifies the physical significance of the wave function, the nature of which deserves its own video. And when these two strands come together, Born's rule emerges naturally. To me, Bohmian mechanics is clearly the most elegant quantum theory. While it contains one more equation than traditional quantum mechanics does, the addition of this equation dispenses with the need for the crutches of traditional quantum mechanics, such as Born's rule and collapse postulates. So it takes quantum theory from being defined in a rather fuzzy way to having a mathematically precise definition. It is mathematically more complex than traditional quantum mechanics, but it also yields a commensurately fuller picture of the underlying reality. So it's hard for me to understand why some people view this complexity as a vice. Bohmian mechanics does not eliminate all the mystery of quantum mechanics, just the unnecessary confusion around observation and measurement. It also highlights what I think is perhaps the deepest mystery of quantum mechanics, non-locality. That's another topic for another video.